Hey, what's up, YouTube? I think we're live. How's it going? It's another day practicing mathematics on the internet. Today is June 22nd. Last time we were in this section, which is my favorite, Chapter 3 on vector spaces. Last time we were working vector spaces was May 3rd. Today is June 22nd, so these cycles are getting longer and longer every time. I'm freaking excited, everybody, because this is the beginning, to me, of abstract algebra and quote-unquote real mathematics in some pretentious, way of saying it. Mathematics changes dramatically, like once you start moving toward proof-based math. It's kind of like a completely different field, almost, not really, but like it is very, very different from what people are used to with computational math. So we're moving into some more abstract theoretical math. We're abstracting the idea of vectors or matrices. First we introduced vectors, then we introduced matrices, and they had some similar properties. Now we're moving to a more general space called vector spaces. And we can see how things like polynomials also satisfy a lot of the same algebraic rules that vectors and matrices follow. It's pretty freaking cool, if you ask me. So, as well as many other types of examples of more abstract vector spaces. Okay, so we are primarily still focused on Fraleigh and Beauregard, but this is the chapter where I start introducing Axler as well. Fraleigh is designed to be a first course in linear algebra, whereas Axler is designed to be a second course. And so we have reset so many times back to chapter 1, and we've reset so many times back to chapter 3 that every time that I come back and do another stream on chapter 3, I want to increase the difficulty just a little bit, or not just the difficulty, but the depth. And to that point, one thing we did yesterday I thought was pretty freaking awesome. Yesterday, this was a Fraleigh exercise, and this was like, dude, this is a proper freaking proof here. We worked a proof from section 2. I don't know why I wrote 1. I'm pretty sure it was 12. Exercise 12. But yeah, as of yesterday, I started relearning LaTeX, and I typeset, this little proof. I feel like it's fairly close to correct. Maybe it's not perfect, but yeah, that was the biggest achievement from yesterday's stream. And it involved me relearning how to write certain things in LaTeX. Like, if you look at the right-hand side of this window, you see the preview, and then on the left, you see the math, or like the typeset markup language called LaTeX, which produces the diagrams on the right. So, for example, to see that the equal signs line up, nicely, that involves like using these ampersands at the beginning, using these double slashes to create a new line. Like, I just started relearning LaTeX for the first time in like 15 years yesterday, and man, it's quite beautiful, but it's also, it feels a little outdated somewhat. So somebody recommended Tips as an alternative, and I might look into that, but I just love that this note-taking app, it's kind of like an Obsidian. I love that this app is available and supports LaTeX. Anyways, my point here is that we are starting to get to proofs. And so, yeah, let's get back to the iPad. Alright, these are the sections in chapter 3. Today I kind of want to try to hit all of them, not just 3.1 through 3.4. These are marked as the required sections, and then the last one is optional on inner product spaces. And then in Axler, we define Rn and Cn, and we define vector spaces, and then we define subspaces. So I want to work problems from both Fraleigh in green and Axler in yellow today. Okay. All right, let's do this. So, Fraleigh, section 3.1 on vector spaces. Cool. At some point, people will start showing up in chat. Oh, yes. Let's do this. Nope, that didn't work. This. Here we go. Here's some footage from Hawaii, from my recent trip to Hawaii. So I hope that this helps. Okay, where is my Fraleigh book? What is the next exercise that we need to work? I'm using paper books because I think that paper is just more productive than digital books overall. But also just because it's a better single source of truth for problems. And like, which problems have I completed? Because I want to work every single problem from this book, which is ambitious. But, nonetheless. Alright, so vector spaces. Determine whether the given set is closed under the usual operations of addition and scalar multiplication and is a real vector space. Okay, so let's see. Determine whether the set consisting only of the number 0 is closed under the usual operations of addition and scalar multiplication and is a real vector space. Okay, so the instructions are for multiple different exercises, but why are we WADA? We're just random Hawaii videos right now. What's up, El Kuki? What's up, Arad? How's it going? It should be updating every minute. Has it been updating or no? Has it just been consistent this whole time? Yeah, it should be updating. What the hell? Alright, what's up, everybody? Now that some people are here, let's get chat up. Okay, so solution. Yes, this is the trivial vector space. The trivial vector space only has one element, the 0 element. So we'll say yes. Firstly, 0 plus 0 equals 0, which is then in our vector space 0. And then r times 0 equals 0, which is still in the vector space for all real numbers. And finally, so that just answered the first part. Closed under addition and closed under scalar multiplication. So now we check the vector space axioms. So this is a good spaced repetition here. We have 4 addition axioms after we show that that your vector space, that we have a well-defined operation of addition and a well-defined operation of scalar multiplication. Like once we have an addition function, and we show that we also have a multiplication function. Multiplication doesn't always have to be regular multiplication, but we're going to take a pair from the field and the vector, and any vector, and then map it to a new vector, which we call kv in your vector space V. Now, yeah, this is a way to write the idea that we have a well-defined scalar multiplication and a well-defined addition functions. And we have that. Now we check the vector space axioms. There are 4 addition axioms, and there are 4 multiplication axioms. The way that this book writes it, and this is how I like to think of it and remember all of these. So which are the ones that are in common? Definitely. So there always exists a multiplicative identity in fields. So I shouldn't say that there exists, but 1 times any vector v is v, must be v. This is an axiom. Even though the properties in a field include like 1 times k for any k will preserve the identity of k, we need this axiom to connect the field to the vector space. So maybe those are just slightly different, but there exists a 0, there exists a 1. These are the additive and scalar multiplicative identities. Then for any v, there is a negative v, which I'm just going to write, as negative v right now. So for any vector, there's an additive inverse. And then these are the ones in common so far. And we have commutativity, which I'm going to write as commutativity right here. Okay. Then, what are these last 2 multiplication axioms? We have distributivity of 2 vectors, which maybe I even say distributivity with vector 1 with 2 vectors. And then we have distributivity with 2 scalars. And because I do want to start working with Axler, I'm going to start writing k to mean a scalar in our field k. Hey El Kuki, have fun studying, bro. Have fun. Good to see you, man. Thanks for stopping by. Okay, so I hope all that looks good so far. How's it going, everybody? I hope you all are having a good freaking day. If anybody is new, hello. It's nice to meet you. Let me know, and I will give a little introduction to myself if folks want it. And what else? I wanted to say, I don't know, yeah, just how are y'all doing? Please treat this like a study with me radio show. So I'm just studying, and I hope that you all are getting something done too. Like, I don't actually expect people on the other side to be actively learning linear algebra. I'm here practicing. I'm practicing linear algebra again and again and again. Because I think it's kind of fun. So, let's check associativity on both. Hey, Luna. You're studying some Algebra 2 today. Heck yeah. Algebra TOO, not TWO. I see. Nice, dude. What kind of algebra? Okay, so let's check associativity. Well, of course, 0 plus 0 equals 0 plus 0, which is the same as 0 plus 0 plus 0. So associativity of addition works. Associativity of multiplication. Let's use R and S. R times S times a vector 0 is equal to, well, any scalar multiple times 0 is 0. So this by definition is 0. And then this is also equal to S times 0, because for any S it is 0. And then this is the same as RS 0. I think that is a perfectly fine way to do it. Yeah. So this one is done. There exists a 0, yes. 0 is the one number in the vector space. And for every vector in the vector space, namely the only point in the vector space, which is 0, then, adding to itself is preserved as 0. Let negative 0 equal 0, then 0 plus negative 0 is 0 plus 0, and that is 0. So that is satisfied as well. Commutativity. Well, there's only one. In general, we want to show A plus B equals B plus A. But in this case, well, there's only the one element, so of course it commutes with itself. Yeah. There's only one element, so anytime that you have a mathematical object with only one element, of course it commutes with itself. Causal duality, never heard of it. Some abstract nonsense higher category versions, but I'm just sticking to the basic case of ordinary rings. That sounds pretty interesting, bro. That sounds awesome. Okay, So 1 times 0 is, well, 0. Yeah. Because again, like, any scalar times our 0 vector. Remember that 0 everywhere is being treated as a vector. But, yeah. Distributivity of 2 vectors. So if I have a scalar, and, well, there's only, again, one vector. So, zero is the same as 0 plus 0, and then 0 is the same as k times 0 plus k times, so 0 is the same as k0, so now I have k times v plus w equals kv plus kw for all vectors v and w in our vector space. Then distributivity of 2 scalars is going to be some third scalar times 0, and then that, by definition, is 0, which is 0 plus 0, and 0 is the same as k1 times 0 plus k2 times 0. So now we have distributivity. This is now in the format of k1 plus k2 times vector v is k1v plus k2v. So these statements seem fairly trivial, or kind of like hard to, like of course, like that seems obvious, or something. Like, why are we even going through the work here? And it's because in higher math we care about precisely proving statements and doing things in like a very logical step-by-step deductive process. So now we have checked every axiom, and this was a fairly straightforward exercise. We did it. Let's do the next one as well while we're at it. So let's do another one. Determine whether the set Q, being the rational numbers, is closed under the usual addition, multiplication, and is a real vector space. Let's think about it for a second. I think I know the answer. Do you? I think the answer is false. So Q with addition is closed, but R, Q, and multiplication is not closed. Another way to write this, I think, would be RQ is not a subset of Q. For example, pi times 1 is pi, which is not in Q. This is in the format now of R times V which is now in our scalars instead of being a real vector space. Hey, it's the cool chapter again. Yeah, dude. And we took our vector V to be 1, which of course is 1 divided by 1, and this is in the field of rational numbers. But RV is not in Q. So, the rational numbers is not closed under multiplication, and then therefore we don't even need to check the rest, because it's not a real vector space unless it's closed under the two operations. Those need to be well defined, and in other words, closed. Cool. I guess you could say Q is a Q vector space. Yes, that is true. That is a good follow-up. But Q is a vector space over the rational scalars. Acting every rational number being multiplied by a rational number is still a rational number, but it's not a real vector space, which is what the book, like this exercise, is asking if it's a real vector space. So this is a case where, as you progress in linear algebra and get to advanced linear algebra, we start letting K be like the field of scalars being different fields, including the rational numbers. So this one would not, the rational numbers are not a real vector space, but they are a rational vector space. Or there are other types of scalars that it would be a vector space over, like the field with 2 elements or something. Z2Z, is that right? Is that how I write the field? Do I write cross? Does it need to be multiplicative? Yeah, it needs to be multiplicative, right? Anyway, whatever. There's other fields that this there are other scalar fields which make the rational numbers a real vector space, or a vector space, not a real vector space. Okay, what context of homology? Yeah, I don't know what that is. I see Q vector space related questions pop up a lot in homology stuff, and I have no idea why. Ooh, interesting. That sounds cool. Okay, then the next question is about the set C of complex numbers with the usual addition of complex numbers and with scalar multiplication defined in the usual way. So, yeah, does the set of complex numbers form a real vector space? Yes. Let's just do it. Let's just do another one. We should see this one. And now, next time that we come back to this section, we're going to get to harder problems because I just worked 3 of them. I will have worked 3. Let's see. I think that these qualify as proofs. Let's see. We say that, yes, C is a real vector space. And this is closure under the usual addition and multiplication. So first, if I write it as C plus C, this is contained in the complex numbers. Let Z1 equal A1 plus B1I and Z2 be A2 plus B2I, then clearly Z1 plus Z2 is A1 plus A2 plus B1 plus B2I, which is itself a complex number. So that satisfies closure under addition. Then now we check whether the complex numbers are a real vector space. And yes, that is also true. Let R be in the real numbers. Z equal A plus BI in the complex numbers. Then RZ is RA plus RBI, and this is in the complex numbers again. So that shows scalar multiplication is well defined. And now we get to the fun part. Hey, Luna. She's been annoying. A1, A2, A3, A4, S1, S2, S3, S4. Let's check associativity of both. I kind of prefer identities first. Let's make this even shorter. Plus identity, multiplicative identity, associativity. We need additive inverses. We need commutativity. We need distributivity. Distributivity of 2 vectors and of 2 scalars. So, for A1, additive identity, clearly, we're going to let the additive identity be 0, then z plus 0 is z for all vectors z. I think that's good enough for now. Associativity, z1 plus z2 plus z3. Well, this is a1 plus b1i plus, after one in-between step, like just rearranging terms, we get a1 plus or wait, no, A2 plus A3 plus B2 plus B3 I. And if we add the definition of addition of two complex numbers, we have now A1 plus A2 plus A3 plus B1 plus B2 plus B3 times I, and that's by applying the definition of addition of two complex numbers. And now we can use associativity of the real numbers here. Take a couple steps, take a shortcut, and then by associativity of the real numbers and a little bit of unfolding, then we get Z1 plus Z2 plus Z3, and that completes associativity of addition. Associativity, multiplicative identity. Multiplicative identity lets the multiplicative identity be 1. In fact, the multiplicative identity always must be your field identity 1. So 1 times Z is 1 times A plus 1 times BI, and that is A plus BI, which is Z. So we satisfy multiplicative identities. Associativity, let R and S be real numbers, then RS times Z is RS times A plus RS times B I. Then again, we have associativity of real numbers. The AS of R is also, there is technically another parentheses here. By associativity of R, then we get R times, and with just a little bit of a couple extra steps of rewritings, then we get R times SZ. And we found associativities. Additive inverse, yep. If Z is in the complex numbers, let negative Z equal negative A plus minus negative A minus BI. Then Z plus negative Z is A minus A plus B minus BI, which is 0 plus 0, which is 0. So we've got our additive inverses. Commutativity. Commutativity works the same, and again, this is by commutativity of the real numbers. So this is somewhat straightforward proof, but it's a proof nonetheless. And for some people like myself who are taking an engineering course and expecting to become an engineer, but then now you're starting to be asked to do these little simple proofs. This is where I was like, yo, wow, that's kind of cool. It's like a nice little Sudoku. Like, this is like it's simple. It's not hard right now, but it's fun. R times z1 plus z2. We want to show that that is r times z1 plus r times z2. This is r times a1 plus a2 plus b1 plus b2 I. This is r times a1 plus a2 plus r times b1 plus b2 times I. Now we have distributivity of the real numbers. Which then gets us to this is, like in a programming language for math called Lean, we then just say that this is simple, and then isn't it simple for like kind of trivial, just like a couple extra steps of rewritings, just like a little bit of basic algebra next. Then we get to RZ1 plus RZ2. But the important part, I at least want to write this proof out to the point of distributivity of the real numbers. Like, I feel like that's getting to that point is, for simplify, not it is simple. Yeah, okay. I thought it was like, it is simple. Here, yeah, okay, simplify. That totally makes sense. Totally makes sense. Are you technically implicitly assuming distributivity in the proof of multiplicative identity? Am I? For this one? Oh. No, I'm not. Because the definition of multiplication is given as the definition, like the usual definition of scalar multiplication is that, like, is defined to match the distributive property of like real numbers, but this is by definition RA plus RBI, right? So it just coincides or something with the distributivity of real numbers. And yeah, all of this follows from C being a field, and I like to imagine someday somebody, if somebody ever rewatched these videos, or if I edited them, then I'm trying to guide somebody toward the idea that, a lot of this all seems to be inherited by associativity, by properties of the parent space, and all of this seems like it could be, like, if you are introducing and talking about the word field, like, is it true that any field is a vector space over itself, or a vector space over a subset of itself? Yes. Like, I'm trying to, like, guide somebody toward those ideas. I don't want to just, like, say that as like the entirety of the proof at this level of math is my idea, because at this level of math you're being asked to like do these trivial but valuable verifications yourself, and that can guide you to seeing deeper structure, I guess. Okay, so r plus s times z is defined as I just mentioned, r plus s times a plus r plus s times b times I. Then now we use distributivity of the real numbers, and we get RA plus SA plus RB plus SB times I. And then, let's see. Oh, now by definition of addition of complex numbers, this is RA plus RB I like, I feel like my proofs of something like this have gotten more technical and precise or something, like having written a little bit of lean, done like a tiny bit of lean formalization, and I'm seeing how like every single rewrite is an application of some axiom, like a little more clearly, like more precisely than I used to. Now this is by the definition of not Z, C. Whoops. This is by definition of complex number addition. And now this is definition of scalar multiplication. Right, and now this is in our desired form, RZ plus SZ. So our property holds. And we are done. So that was the trickiest. I mean, it's still somewhat pretty straightforward, but there was like a little more to check along the way than the trivial. This is in math we call often like a space that's completely empty or a space that only has one element. We often call these like a trivial space or a trivial vector space. Because in the definition of a vector space, part of it includes the fact that 0 must be in the vector space. So then this is the smallest possible vector space because it only has one element, the element that was guaranteed in our axioms. That's the only element that's guaranteed to exist as a vector in the axioms, and then everything trivially holds. This one was just like a little trickier to think about, but we could see very quickly that it fails scalar multiplication. But we had this follow-up idea that maybe, I mean, it is a vector space over itself if you change the scalars to integers, well, yeah, finite fields or, finite fields or frickin' complex, rational numbers. And then this one, our intuition said very quickly, yes, this is going to be a vector space, but to actually work through the precise, rewriting steps, every step along the way, and justifying every step, at least verbally right now. I'm not writing out these proofs in Lean or in, freaking LaTeX right now, but okay, let me read what's going on. Simplify, because it runs that makes sense. It just runs an automatic simplifier. That makes sense. What's up, Zafarb? How's it going, bro? Have a feeling that research has a backwards flow from learning through books. In books, it's definition, then theorem, then exercise. In research, it's problem, then confusion, then new definitions, then yes, that sounds 100% right, which is more like what the real world is. Like, I have a problem I want to solve, and then you build the theory, and then you find some solution to that problem, and then once you have the time, you start cleaning up your solution to a more abstract, more simplified abstract theory, that solves not just this problem, but then other problems as well. I'm thinking of software very much, but I imagine that research is exactly the same way. Like, Galois was like, we can prove these statements about polynomial equations. And then we took his basic ideas and then looked at other spaces where we can apply the same ideas. Or something like that. Ooh. Free vector spaces. I don't know anything about that. Yeah, totally, dude. I think every math student can benefit from learning a tiny bit of Lean. Yeah, dude, I think every math student should do just a little bit of Lean. What do you think? Like, in a Intro to Proofs course, do you think... I assume you've taken an Intro to Proofs, right? Like, you're doing research, right? No. Arad... Man, I'm thinking of Zafarb is doing undergrad research. Arad is a grad student. Is that right? I forget, man. I apologize. But I think, dude, that, I think all of you have taken an Intro to Proofs course or at least learned that material. In a course like that, do you think that the entire course should be taught with Lean nowadays? Or just, a little module? That's my hunch, is, maybe at the very beginning, just a little bit of Lean. Or, most of the course being... traditional classical pen and paper proofs, but maybe one Lean exercise in every problem set, or just the last couple of weeks or something, at the end of the course, okay, we just spent the rest of the course doing this by hand. Now check this out. This is where modern math is going to start moving toward. Let's do some very simple, let's prove the natural numbers using proving piano arithmetic facts. Work through the natural number game or something. I feel like at the end of a course, having a module on Lean formalization would be really cool for an Intro to Proofs course. Note that an axiom requiring 0 in V doesn't automatically guarantee 0 as a valid vector space. You have to make sure it is consistent with the other axioms too. That's interesting. I thought... okay. Why wouldn't... Addition and scalar multiplication, doesn't that then give you 0 being a vector space? Like, I feel, yes, like, this is the most important thing that you need to show. Because if you have a vector space and multiplication as something that takes you into, like, gives you a non-zero number, you see what I'm saying, right? Then, yeah, that's not a well-defined or closure under scalar multiplication. You definitely need to do that. That's what I would guess, but I could be wrong. Analysis gameplay, algebra gameplay, 0 plus 0 equals 0. Yeah, algebra is very fun because it's at the beginning of courses or textbooks, it's like, let's prove that 0 plus 0 is 0. Let's prove that 1 plus 2 is 3. And, like, really simple seeming facts, but you have, like, there's actual work to be done there to show that 1 plus 2 is 3. That's pretty cool. Just toward the end of undergrad, so not quite yet. I don't think it should be entirely lean because there's a lot of mental overhang, especially if you don't have background in coding. Yeah, I'm definitely biased. Like, I have bias and blinders because I've done a lot of coding. In particular, I've done a lot of static typing coding, like with Swift and functional programming. So to me, lean is, like, very natural. It's like, a little more hardcore and cool, but I think it would be a lot to try to teach an entire course with lean at the same time. Like, there's 3 different options, or 4 if you consider just do nothing. Like, option 1, just do nothing. Just keep teaching intro to proofs, with pen and paper, no frickin' computers involved. I think that's a valid option, and I think that there's an argument for that. I think that there's a strong argument for that. Option 2 would be run an intro to proofs course where every single exercise is formalized in lean. That doesn't seem very valuable. I don't think that you'd get as far in proof skills, even if you do get fairly good at lean proofs. If students would get good at writing lean, which can be a valuable skill, but I don't think that you'd get as far in mathematical maturity and being able to write and read math in the traditional way. Option 3 would be lean as an afterthought throughout the course. Like, maybe one problem in every problem set. Say every problem set is just arbitrarily 10 problems. Have one simple proof that you're asked to solve on paper and in lean, and then 9 more traditional proofs, right? Like, maybe a simple proof, also formalized, but do that throughout the course. And then I feel like the last option, which is what I would lean toward, would be like the last month of the course or the last week, maybe. Just kind of like bonus lectures at the end that are not even on the test, maybe. Yeah, probably just like the last week or so while students are freaking studying and, cramming for finals and they can't absorb new material that's going to be on the test. Just do like a freaking intro to lean that's just like a culmination of the course. Like, do a whole traditional classical proofs course, and then at the very end just be like, by the way, here's how modern mathematicians are starting to write the exact same proofs that you've been working throughout the semester. Yeah. So, option 1, do nothing. Option 2, go all in. Option 3, mix it in throughout. Option 4, just like an afterthought or something, or like a teaser at the end. There's only one possible definition for addition and scalar multiplication. The only slightly non-trivial part is to verify that identity, distributivity, and stuff are satisfied. But what I mean is that, yeah, I mean, of course, there's only one way to do this, but like if you assume K is a field, that K is any field, and 0 plus 0 is 0, and K times 0 is 0. Now, like any element in your field times the 0 vector is 0. Then I think that you get all of the rest. I think that you can, given these assumptions, then I think that the other axioms hold. I mean, this is an interesting question, right? A1, associativity, S1, associativity. I mean, dude, like, associativity of addition, well, 0 plus 0 plus 0 is 0, and you can rebalance your parentheses, right? Like I'm being kind of sloppy, but you know what I mean by that. Associativity of scalar multiplication. Rs times 0 is 0 is Rs 0, right? Like, my point is that I think that the other axioms all automatically hold if you have just those three pieces. Oh, yes, yes, you do need to prove it. Sure, absolutely. Yeah, totally. Yes, I thought you were saying that there are cases where it's not the case. It's like, well, I mean, as long as your addition and scalar multiplication are defined correctly, then it's always a vector space. I see what you're saying. Yeah. For all of, at this level of math, like everything needs to be proved, even these trivial seeming statements. Yeah, that's how math is built. Yes. I mean, that might be... I wonder if that's an exercise in this book. Like, instead of saying the set 0, where 0 is a number, is the real number, I wonder if it says anywhere like the set, let V be the set A, or like the string A or something, like with only one point, like so that we just slightly move away from the idea of it being 0 in the real numbers, and then show, or like find criterion for V to be a vector space or something like that. I wonder if that's an exercise. I mean, it's kind of trivial, but... Okay. Not... Maybe in the true-false. Okay, whatever. Let's keep moving on. 3.2. I think a better example is fields. The axioms of a field requires at least two elements. Yeah, 0 and 1, right? And there's multiple ways to define addition and multiplication on two elements. Yes, that makes sense. Yeah. But there's only one that satisfies the field axioms. Yeah, that totally makes sense. Yep. That's like a better case where you have to... Yeah, because there's not just one point, but multiple. So... Okay, yeah. 3.2. Basic concepts of vector spaces. We could move on here, or we could try to interleave Axler. Let's go here first. Basic concepts of vector spaces. Determine whether dependent or independent. Dependent set 1, 4x plus 3, 3x minus 4, x squared plus 2, x minus x squared in P. Okay, so we've already learned about the idea of dimension in chapter 2. So I believe that this section is going to have a theorem or something, but I would say a claim that a set S is dependent if the size of S, if there are more elements than the dimension of the vector space. Note that in our example, S is a subset of the degree 2 polynomials, which then is a subset of P. So we could consider... We can consider this as like, we could consider whether they're dependent or independent in the infinite dimensional or in all finite dimensional polynomials. 1, 2, 3, 4, 5. The size of S is 5, and the dimension of P2 is 3. So S is dependent. I can use this proof if we have this claim proven somewhere else, either in my previous homework examples or in the section, if this is a theorem. Are we? Yeah, we are. Unfortunately, we're skipping the epic subsection. Unfortunately, dude, because I'm trying to work through all the problems in order, for better or worse. Because this crossed my mind that in the method in which I'm working through this book, I'm not reading the sections until we need to. And there are exercises on that epic optional subsection but they're near the end, I think. Exercises 26 through 29. So I hope we can get there in not too long. Truly a constructive proof. Is it? Yeah. I mean, what you're saying is a more constructive approach, or one constructive approach. This is kind of like proof 1. Oops. A more constructive approach would be to find find a dependence. If I can find a dependence on these vectors, then I know that I see one, that the set is dependent. So if I labeled these as V1, V2, or since they are polynomials, I shouldn't just say vectors, but P1, P2, P3, P4, and P5, I see that P3 and P2 are very similar, right? They're both polynomials with one x term and one constant term. So I think that I can build the dependence of P3 on P2 and P1. So I claim that P3 is A times P2 plus B times P1 for some AB non-zero. For some non-zero AB. So this is my goal right now. Note that P3 is 3x minus 4, which is 3 times x minus 4/3, which is 3 times 4 over 4 times x minus 4/3. I'm trying to get 4 multiplied with x. I'm trying to get that 4x term from P2 out of P3. So this is now 3/4 times 4x minus 16/3, right? Which is now 16/3 is itself, wait. 4x plus 3 is the format of this term that I want. Ah, shit. Is this the right way to... Maybe there's a cleaner way. Like, I'm trying to do this one by inspection, but 4x plus 3, if I add P1 to that, then this is 4x plus 4. I think that there's a cleaner way to do this. maybe I use this fact. 3x minus 4 is 3x plus 3 minus 7. I don't know where I'm going with this. I don't want to immediately jump to the augmented matrix approach, but I might do that. I think that's in the next section. Damn it. Okay. Better approach would be if I can, I think, build x as some combination of these polynomials and 1 as a combination of polynomials, then I really quickly have a dependence for the third. Or okay, yeah. So if I can get 1x and x squared, P3 would be x plus 7. So x plus 7 minus 7p1. Here's 4x minus 3x is x. 3 minus negative 4 is 7. So yeah, there's an expression of x, and then x squared I see is p4 minus 2p1. So I have 1x and x squared related to p1, p2, p3, and p4. Then p5 is x minus x squared, which is p2 minus p3 minus 7p1 minus x squared, p4 minus 2p1. And now I have p5 expressed as a combination of the others. And we should be able to reduce this further, but that would be enough to show that the set is dependent. So let's find it. It would be 2p1, positive 2p1. Oh wait, no. Positive 2p1 minus 7p1, negative 5p1. I'm looking for all the p1 terms, and then I'm looking for the p2 terms. We have 1p2. Now the p3 terms are just minus p3, and the p4 terms sum to negative p4. Then now I have a dependence relation. Hey, what's up? Lakshmi How are you, dude? How are you? Explicitly showing dependence would exhibit an actual linear combination that sums to 0. That's it. That's right. Yeah, we want a sum that sums to 0 with not all coefficients equal to 0. I knew somehow I needed to say that the coefficients are not all 0. Yes. So even better, 5p1 minus p2 plus p3 plus p4 plus p5 equals 0. This is a dependence relation. There we go. That's even better. So S is dependent. Yeah. Yeah, I feel that the previous approach had a solution, but I got somewhat stuck and paused on it. I was getting confused by the math here. Yeah, this should have been 4x minus... Because I want to rewrite that as 4x minus 3, right? Or 4x plus 3. So this approach could have been like 4x plus 3 times negative 16/9. I don't think that that's exactly the right way, but it's something like that, dude. Yeah, I would add the right number of ones of the constant. 4x plus... wait. 4x plus 3 minus 3 is what I would want to do here. 4x... Yeah, okay. I think that this is the way to revive this last approach. This would be 4x plus 3 minus 3, because those sum to 0, minus 16/3. And then this is 3/4 times 4x plus 3, minus frickin' 3/4 times 3 plus 16/3, and this is 3/4 times the second polynomial, and then this multiplies to a number. 9 plus 16 is 25. 25 times 3 is 75/4 times 1, which is P1. There we go. I knew that there was a way. I just kind of blinked for a second there. Yeah. The goated math trick, add 0. Yeah, the goated math trick. I did that. It is a goated math approach in algebra. Just add 0 and then rewrite that as 3 minus 3. That's what I did. Heck yeah, I got it. Adding 0 is so overpowered for literally no good reason. Yeah, I feel like, I don't know if you've played any, card games, I don't know. I'm really into a campaign-based game right now called Earthborn Rangers. Phenomenal game. Amazing, beautiful game. I feel like I could stream it. It would work as, a solo game. Let me try to write the next problem as I talk. But there's some variants of playing certain tabletop games where you take a handicap because one card is just way too powerful, or in Magic the Gathering and others they'll nerf cards because they're just too OP. I wonder how much of math you could just as a challenge, don't use tricks like add 0. Like, can you like take out that strategy because it's just too damn powerful? Yeah. Adding 0 is so overpowered for no good reason. Okay, so we got 3.3 coordinatization of vectors. I'm just going to write that. Find the coordinate vector of the polynomial. So I'm going to adopt the notation from another book. So find the coordinate vector of x3 minus 4x squared plus 3x plus 7 relative to the ordered basis b, where b is it is a sequence, not a... Well, yeah, I don't know. Where b is... Oh, shit. Why b prime? I don't know why he writes b prime, but I guess just to really note that it is not the standard basis, maybe. X minus 3, or x minus 2 quantities cubed, x minus 2 quantity squared, x minus 2 and 1. Neat. Okay, so powers of x minus 2 of the vector space P3 of polynomials of degree at most 3. Use the method illustrated in example 5. So I believe that first we represent, I'm going to call this, I don't know, let V be that vector. And let B1, B2, B3, and B4 be our basis vectors. So I could say, like, let B prime equal the set, or the ordered sequence, BI, and as usual, E is the standard basis, EI. What is the standard basis? I forget, because I don't know if there is a standard basis. Like, does it start with the constant term or the x to the n term? So I feel like I shouldn't use standard because I don't think that there is a single standard for this. And B be the standard basis, or this basis. I guess in this approach I should give these primes, if I'm going to do it this way. Then B1 prime is using a good old binomial theorem. X cubed minus 6x squared. Oh wait, no, minus 2x squared. Ah, shit. Oh, Pascal's triangle. All right, 3, 3, 1. Yeah, so 3 times negative 2 is negative 6, the way that I thought it was. Yeah, negative 6x squared plus 6x, I believe, minus 8. Oh, wait. No, 2 squared should be times 4, right? 4 times 6 is 24. Dang it. Alright, so x minus 2 cubed. I need to really just drill these binomial expansions. X minus 2 squared is certainly x squared minus 4x plus 4. And then this is x cubed. Yeah, something felt off. Something felt wrong about my numbers. And x squared terms, we've got a negative 4x squared minus 2x squared is negative 6x squared. And then x terms, we have 4x plus 8x is 12x. 4x plus 8x is 12x, and then minus 8. So I did this off by a factor of 2. So, and then, I can write this first basis vector relative to the standard basis as the coordinates negative 8, 12, negative 6, and positive 1. I prefer for the coordinates to go in the same order as the powers. The order doesn't really matter for this. It's the same basis. I know that it doesn't, I mean, it matters. Yeah, take out axiom of choice. It's too powerful. Yeah, I mean, math does do exactly what I was describing. Like, mathematicians do that, like, handicap math. Like, restrictions, of course. But, like, are there others just in, like, exploring, like, algebra proofs without something much more mundane or, like, less fundamental? The order matters when you're writing coordinate vectors, right? The order does matter. I mean, it's arbitrary. You can write it in either direction, but it matters if I'm going to write a matrix that I can simplify, right? I screwed up a thing. So, I can rewrite we find the coordinate vector of the vector that we're interested in relative to this secondary basis via solution of the matrix how do I write this again? The matrix of the new basis relative to the old basis times some coordinate vector relative to the new basis which equals the coordinate vector relative to the old basis? I feel like I wrote that not exactly correct, but I know for sure we write out the coordinate vectors relative to the standard basis in columns. B1 prime relative to B is -8, 12, -6, 1. Coordinate vector of the second basis vector relative to the... Yeah, all of these I've lost my x cubed terms. Shoot. Yeah, what am I doing? My x cubed coefficients. Okay, so -8, 12, -6, 1, 4, -4, 1, 0, -2, 1, 0, 0, and 1, 0, 0, 0. Solving with the coordinate vector of v relative to the standard basis would have... I'm just trying to match the same ordered basis that the book uses for polynomials. I would swap the order of these, but oh well. 7, 3, -4, 1. Seventh, +3, -4? Yeah, 7, 3, -4, 1. interchange the last row to the top. Oh, goodness. Add 6 times the last row to the third row. And then put that in the second row. So 6 times the fourth row plus the third. So 6 plus -4 is 2. Subtract 12 times the last row from the second row. So 12 minus 12. -4 minus 0. 1 minus 0. 0 minus 0. 3 minus 12. Add 8 times the fourth row to the first row. So 8 minus 8 is 0. And now 4, -2, 1. 7 plus 8 is 15. Add 4 times the second row to the third. 8 plus -9. And then add the third row to the fourth. Therefore, our coordinate vector relative to the new basis is 1, 2, -1, 5. Is this in the back of the book? Ooh, yeah. Reordering the basis will reorder the matrix. Yeah, it's not a big deal, but you just need to make sure that you're consistent, of course. Constructive algebra, where you don't use things like the law of excluded middle and double negation elimination. Hell yeah, hell yeah. What's up, Pumpkins? Good to see you, dude. Good to see you, Pumpkins. How are you? Man, I want to get better about limiting to only 2-hour streams. We're coming up to that time. So we've got 15 minutes left if I'm sticking to 2 hours. Let me double check my calendar. Do I have anything going on today? Oh, shoot. Okay. Nothing going on today. Heck yeah. Heck yeah. Oh, y'all. It's good to see you all. Thank you for tuning in, hanging out with me. I know that we're in the fun chapter. Maybe we try to do an axler proof instead of moving on to the next sections. I kind of feel it's more important to start working in axler than it is to do even more Fraleigh. 3.3, problem 11, 1, 2, -1, 5. Yeah, we got it. Cool. Nice. Well, 3.4 linear transformations. I wonder if it'll be fast and I can just like try to rip through it. 3, 4, because this is where this stuff is all getting so cool, right? Linear transformations. A linear transformation will map between vector spaces. We're talking about maps between vector spaces. And we're getting some cool shit. Okay, so use the preceding information, summary item 10, and your knowledge of calculus to find all solutions. Find solutions in infinite differentiable space of the given differential equation, y double prime being negative cosine x. Yeah, let's see. A solution will satisfy how did these go again? Solutions satisfy like a particular solution plus elements in the kernel. How does this one go? If y double prime is negative cosine x, then what's wrong with saying that y prime is negative sine x plus c, and then y is cosine x plus cx plus d. Is there anything wrong with that approach? I mean, it's like a fairly simple differential equation. There's not like a combination with y. It's just y double prime. Is there something wrong with this? It's an odd problem, so I can just check. These and yeah, like for all f of the form cx plus d, then f prime is c and f double prime is 0. So f is in the kernel of t, where t is double differentiation. 3.4, problem 11. I'm pretty sure that that's correct. Anything wrong with this? Yeah, c1x plus c2 plus cosine x, such that c1, c2 are in R. Yeah, so that's just a nicer way to write the same thing. The set of all solutions is C1 plus C2x plus plus C3 cosine? Yeah, C1, they wrote C1x plus C2 plus cosine x. Yeah, it needs to be one particular solution. Yeah. C1x plus C2 plus cosine x, such that C1, C2 are real numbers. So the kernel of the second order differentiation of double differentiation is a two-dimensional vector space. The kernel is a span of 1 and x. Any combination of 1 and x on double differentiation will be 0. Yeah, okay, simple enough. Yeah, find one particular solution, one particular non-homogeneous solution and add it to the homogeneous solutions. Yes. So there's like multiple homogeneous, and every homogeneous solution, it can be a any constant times each of the basis vectors of the homogeneous solutions. Something like that, I think. Okay, yeah, well, we did it. Then we did, I think, all of the required sections. Let's skip the optional section and let's see if we can take a look at the next exercise in Axler. Heck yeah. Heck yeah. Can we get one Axler proof? Be right back. Okay, I'm back. Do one from definition of vector spaces or a problem from subspaces. Let's just do another one from the definition of vector spaces. Or if I'm truly working breadth first, I've solved one from section 1b. I've solved a couple from section 1a. So we should try to do... No, I've solved one from section 1a, one from section 1b. Let's do the first exercise from section 1c. The iPad has not been freezing or lagging today, right? Like you all, I don't know how closely anybody's watching this, but for anybody who is watching, have you seen any lag in the iPad? Because I think I made some changes that will improve that situation. For each of the following subsets of F3, determine We'll do these one at a time. The set of x1, x2, x3 such that x1 plus 2x2 plus 3x3 equals 0. Okay. For each subset, determine whether it's a subspace. So subspace, we need to check if it's closed under addition and whether it is closed under scalar multiplication. So we're checking both of these properties. And I don't think so. So let here, this is even better. Let's label that space W as I implied a moment ago, and then I'm going to say let X and Y be in W. Then X plus Y is X1 plus Y1, X2 plus Y2, X3 plus Y3. And we check if X plus Y satisfies the rule for W or something. Really, we check if X plus Y is in W. So then the first coordinate plus 2 times the second coordinate plus 3 times the third coordinate this is by rearrangement, x1 plus 2x2 plus 3x3 plus y1 plus 2y2 plus 3y3. And then because x and y were both in W, we know that both of those properties, or both of those terms sum to 0. So then, therefore, x plus y is also in W. All we've checked is, so far, is closure under addition. Then now we're checking if F3W is a subspace of W. Let X be in W and K be in the field of 3 elements. Oh, my bad. This isn't the field of 3 elements. It's any field to the 3rd power. And in this book, F we treat as either R or C. but I think that Axler means to kind of imply that F is any field. So I'm going to try to work with any field, but this is, wait. No, what am I talking about? My bad. K is a field element, and then, yeah, x1, x2, x3, oops. I think everything in my proof still worked out the same because we're just using field properties in the distribution and associativity applications. So more formally, like this is distributivity, then associativity applications to rearrange. Okay. So let X be in W, K is in F, then KX is KX1, KX2, KX3. And KX1 plus 2 times KX2 plus 3 times KX3 is equal to KX1 plus, here we use associativity of scalar multiplication. Then we use commutativity to get K times 2 x2 plus K times 3 x3. For some reason on this one I wanted to show all of the steps and like the entire rewritings, which makes sense, I think, to do properly sometimes. Like at this level, the point is to carefully write out all of the justifications. So first we use commutativity, then we use associativity again for both of those terms. And then we use distributivity. And this is over the field. Like, we're really using these properties, commutativity, associativity, and distributivity, in the field. Now, because X was assumed to be in our subspace, or in our subset W, then x1, x2, x3 satisfies, that sum equals 0. Then in any field, K times 0 is 0. So then therefore kx is also in W, so W is closed under scalar multiplication. So we got both of them, and then therefore part A is a subspace. That was just part A. There's 3 more of them. Let's see what we can get done. X1, X2, X3. X1 plus 2x2 plus 3x3 equals 4. Can I quickly construct an example, like a counterexample? Because if I can show a counterexample, then I show that it's not closed under addition or scalar multiplication. Let's go with note that 0, 2, 0 is in W, because 0 plus 2 times 2 plus 0 is 4. Then let So we check closure of addition. My guess is that this shouldn't work. X plus X is 0, 4, 0. And 0 plus 2 times 4 plus 3 times 0 is 8, which is not equal to 4. So X plus X is not in W, and then therefore W plus W is not a subset of W. W fails closure of under addition. So we'll give that a big ol' X. That one is not a subspace. Part C. Let W. I'm using the label W, but the book doesn't. Again, X is in F3, such that X1, X2, X3 equals 0. Interesting. I think that this is... I don't know if it is or not. I feel like it's not. Can't I construct... Yeah, it's not. Note that 1, 0, 0 and 0, 1, 1 are both in W, Because if you multiply those coefficients together, then they multiply to 0. So they're both in W. So, I don't know, let the first one be V, and lowercase v, lowercase w. But v plus w equals 1, 1, 1. Is not in W because 1 times 1 times 1 is 1, which is not 0. There we go. That one is not a subspace. And then part D, again, three-dimensional vectors such that x1 equals 5x3. I believe that this one will be, because this is defining a line in F3, right? Yes, so let x and y be in F3, then x plus y satisfies this stuff. Then x1 plus y1 on the left-hand side, because x is in W, then x1 equals 5x3, and since y is in W, y1 also equals 5y3, and then this is 5 times x3 plus y3. So therefore, x plus y does satisfy that property that the first coordinate equals 5 times the third coordinate. So it is closed under addition. Secondly, we check if this subset is closed under scalar multiplication. Let k be in F, x be in W, then kx is kx1, kx2, kx3, kx1 equals k times 5x3 equals, by associativity, k times 5x3 equals 5k x3 equals 5kx3. So kx also satisfies the rule for being in the subset W. That the first coordinate equals 5 times the third coordinate. So then therefore, this thing is, what color did I use? Yellow? Yeah. Therefore, this one is a subspace. Therefore, I'll say that. Therefore, W is closed under vector addition and scalar multiplication and is therefore a subspace of F3. And another book uses less than or equal to mean subspace, which is a cool notation, I think. I think that's a great notation. Yo, what's up, Leroy? How's it going? Wait, but F3 is not a field. Yeah, I think I fixed it. I broke something. I finally finished formalizing 2 whole sentences of my textbook after 1 whole week of headbanging. 441 more pages to go. The real question is why? Why are you doing this? Why are you formalizing your textbook? I mean, that's awesome. Are you contributing it anywhere? Are you like upstreaming it, opening like PRs to MathLib, or is this just an exercise for you? Have other people formalized this textbook that you're interested in? You know, because either approach is valid. It's fun to do exercises. I'm working these exercises, even though lots of other people have worked these exercises. You know, exercises are fun. They stretch your brain. It's good for your brain. What's up, Leroy? Speaking of things that are good for your brain, I'm going to go practice some classical guitar now. Thank you, everybody, for watching this and hanging out with me. Oh, it's not in MathLib, so you... so it's a personal exercise I can do while using MathLib and not being completely trivial. Well, you should consider upstreaming it, I guess, is what I'm suggesting. Like, yeah. I would love to contribute to MathLib someday. Like, if I could... I don't know. Maybe contribute during, like, summer breaks or something. Like, while teaching. I think that'd be pretty awesome. You know, or if I hit the frickin' lottery and found a sustainable way to do content creation full-time, like streaming, which is, you know, not expected. Yeah. Like, it would be awesome to contribute to MathLib someday. Yeah, there's so much reviewer work. None of this was specialized for MathLib style guides. Oh, dude. That sounds like something an LLM can help you with. Like, bro, LLM should be able to help, especially a statically typed functional programming language like Lean. Like, bro, like a strong, beautiful type system plus LLMs, like, that should be trivial nowadays. Like, all of my proofs on this iPad are fairly sloppy. They're kind of like the notebook. They're the first draft, but I know that I could sit down and type them out and it would be more textbook formal. You know, and that's just not really worth the time to do all the time. Similarly, I think that we should be writing software in kind of like a sketchy form and then tell the machine to frickin' formalize it and get like a more, you know, all the T's, cross all the T's, dot all the I's, etc. You locked in so hard, like nobody has ever done before. Also known as I ate dinner, fully concentrated. Nice. It's not just one major theorem, it's a whole field of math I'm formalizing. Well, that sounds fucking awesome. I hope that you can try to find a way to share it with others somehow. Because, like, MathLib is just such a cool effort. It's just such a dang cool effort. Photography by kids. Thank you for watching. Thank you. Y'all, please do like and subscribe. It helps the channel just so much. Like, if you haven't already, just take a moment to check if you're already subscribed. Check if subscribed. tomorrow, more linear algebra. We're going to be doing determinants. I know, to Sheldon Axler's disdain, to his pain. Determinants tomorrow. Let's see. If anybody wants to really help me in my journey as a creator, there's like several options. Here are some totally free options. Subscribe to my second channel, jcpractices. It's where I practice classical guitar, which is what I'm about to do. I'm going to play you a song right now. That's one option. Secondly, just like leave a comment. Just thanks or whatever. Just literally, if that's the only thing, just say thanks in the permanent comment section of this video. Of course, you could share with somebody else who you think might be interested in this. That always goes without saying for YouTube videos, but it's particularly true, I think, for live streams, because the more that we build up a community of people who know each other in the chat, like the more fun a live stream becomes. So that one like really helps benefit you too, because like you can hang out with your friends or your teachers or your students in the chat, which is cool. And then appreciated but never expected are monetary ways. Appreciated but never expected would be options like buy me a coffee. Right there in that platform, I'm at jcpractices, and it should be a link in the description. Or second channel, super chats, super thanks, tips, right? That's an option. This channel is not yet monetized. Otherwise, I'd just say, that's the easiest way. So either of these approaches would be at jcpractices, either buy me a coffee or the second channel, both jcpractices. What else was I going to say? Totally free. Another option that's totally free, join the Discord. It's a fun little nice community, I think. And it's a way to kind of connect with each other and try to build up a math community within, my Discord group. Appreciated but never expected would be paid ways. Was there something else I wanted to say? Yeah, thanks. Just thanks everybody for watching. Let's play a classical guitar song. Ooh, yeah, MathLib has a very slow process. Yeah. Well, you could be like Machizuki, right? Like you could just like drop a bomb and just be like, yo, check this out. Here's a giant pile of work for you all to verify. Doesn't learning happen when you fumble trying to solve exercises instead of review? Something I've wondered about spaced repetition technique. Yes, I think that right now these exercises are a little simple, but I'm not just doing spaced repetition on the exercises themselves, but also spaced repetition on trying to teach and explain out loud and get through a bunch of exercises. I don't know if this is the most effective way. Like, it is starting to feel like I'm getting through some like some of these first sections or chapters of Fraleigh are starting to get easier. So that's why I'm starting to add Axler and like increase the difficulty level and get to more depth. So like if there's anything that I would say that I would criticize for my approach on learning or relearning math is that space repetition plus breadth first search, like, I don't think that I should be doing an exhaustive search and solving every exercise. The more effective way, if I was maxing my time on, if I was optimizing for learning math, I would only be doing the exercises that I felt would be challenging. But I'm also at the same time trying to build a YouTube channel and try to stay familiar enough, for newcomers to be able to jump in. And at the same time try to practice the exposition or technical sides of exposition. I don't know if I really sweated at any point today, so it does feel like this may not have been the most effective approach, but there were little things where this time around I tried to practice writing in Steinberg's notation. Like, is this even correct? Is this the right way to write it? Yeah, I was close on that. I don't know. And some of these things, like, I had to recall and, like, think back to, like, what was this again? In Anki, for example, which is a really good space repetition app, you don't quite as linearly come back and review the same topics. If something consistently you keep self-rating as easy, then you jump forward, or like the cycles become much longer. It's not just like 2 days longer till the next time you review a card. It's like, say that you have topic A that's easy, you review it tomorrow. If it's still easy, then you review it in 10 days. And then if it's still easy, then you review it in 100 days or something. It does a much better job of like spacing, of like increasing the spaces in your repetitions. So my naive space repetition algorithm is just increase stream lengths by 2. I might start adding in. I've been thinking a lot because right now I'm excited and hopeful for a middle school role, and I'm not currently practicing teaching middle school level math. I have series on high school, college, and grad school, but I'm not practicing how to explain more fundamental, more basic math. So I think if next reset we added in an entire other series of middle school math, this might bother you all, I don't know, but I think working through basic mathematics, and you all can try to complicate this sort of stuff and like formalize it as we go or something, but like do middle school and simpler high school math. That would add more space to all of my repetitions. I don't know. I'm really trying to figure out the right way, but I think I should be jumping to harder problems. And it's partly why I solved like 3 or 4 Fraleigh exercises in that first section, because it was like, dude, next time I want to get something harder, like let's just rip through these 3 all at once today, and then next time that we come back, we're going to get to more challenging exercises. All right, anyway, Anyways, thank you. Thank you for watching. Let's play... something public domain. This one is a little rough sometimes. This is going to actually be potentially sloppy. Let's see how it goes. This is a Renaissance piece by John Dowland, originally written for the lute. It's a lovely little tune, I think. And we should probably go to Hawaii for this one. So this is my scene. This is how it looks in the guitar stream. And this should have also turned off the background music. Alright. Do it. Thanks, everybody. This is called My Lady Hunstan's Puff, and it's a Renaissance piece originally written for the lute. Such a chipper tune, I feel. Such a chipper, fun piece. Thanks for watching. I gotta go. Wait, is the math stream becoming a guitar stream? There's just a teaser. I just want to make it a thing. Like at the end of the math streams, maybe I always play a piece. If you want to watch me practice some classical guitar, we're gonna go do that in my second channel in just a second. I haven't set up any kind of redirect, so I will just leave a link right here. If somebody else... Is Kay streaming yet? Does he have streaming privileges back yet? Is anybody streaming? jcpractices. Guitar channel. And I don't see anybody on my watch list. All right. See you there. I'll be online in like 15 minutes, I think, on the guitar channel. Thanks for watching. Bye. Bye.